Solving exponential equations. Okay, as the title would suggest, we will be solving some equations, but these are going to be exponentials. And the stuff's a bit tricky. Let's suppose we had an equation that looked like that. What we're being asked is, what exponent do we raise 2 to get a 5? And you probably don't know what that number is. Okay? The way that you're really going to be able to solve equations like this is going to happen in the next unit. So there's an inverse operation to exponentials, which is called logarithms. And that's going to teach you how you can solve a problem that would be like this. For today, what we're going to look at is a very particular case that we can apply this rule to here. What it says is that if you have a b value raised to some power set equal to that same b value raised to a power, the only logical conclusion is that those powers are equal to each other. For example, if I have 3 to the 5th power, and I know that that's set equal to 3 to the y power, there's only one logical conclusion here, which is that y must be the number 5. You can't raise 3 to a different number and still get back the same thing you'd get if you raised 3 to that 5 power. Okay, so all of our examples are going to fall along that sort of logical idea. The more complex ones, we'll look at those in the next unit. Okay, so to start things off, example 1, I have a bunch of different numbers, but all of these numbers can be represented using the base 4. By the way, this is all a setup so that you can answer problems like you can see here at the bottom of the screen where you have different bases. Okay, so our instruction is to take each of these things, each of these numbers, and to represent them as 4 to some power. All of them have to be 4 to a power, 4 to a power. 16, that's going to be your easiest one here, 2. 4 to the second power is 16. Okay, now your next, 1/16, it still has a 16 in it, right? There's a connection there. I hope you remember that if you use a negative exponent, you can create reciprocals. So if I took 4 and raised it to the negative 2 power, I'm going to get the 16 from the 2, but that negative is just going to flip it over and give me the 1/16. 64 is 4 cubed. That is a very good one to know if you don't already. It is also true that 64 is 8 squared, but what we need in our problem is to have a base 4. So 64 happens to also be 4 to the 3rd power. All right, next 2, getting a little bit trickier here. 2 is actually smaller than 4. I mean, 1/16 was smaller, but that was a reciprocal situation. The 2 is actually just a smaller number than the 4, not from being a reciprocal. But recall that 2 is actually just the square root of 4. And radicals, or square roots, cube roots, etc., all of those are just inverses of exponents. If you use the exponent 1/2, that's the same thing as a square root. So 4 to the 1/2 power will bring you down to a 2. Okay? So some weird things, right? We're going to see. Remember that negatives are reciprocals and then fractional numbers are actually like radicals, and they can both be used in a sense to shrink numbers down. Okay, so 8. Oh, 8. Got an interesting one here. The trick to 8 is that you're going to shrink the number down lower than you need and then build it back up. All right. Remember this, that 2 to the 3rd power is 8. That 2 cubed is 8, right? Or if you took the cube root of 8, then you'll get 2. But I want you to remember it this way, that 2 to the 3rd power is 8. And the reason I think that that's going to be helpful here is because we already know the connection between the 4 and the 2. That if I take 4 and I raise it to the 1/2 power, I can bring it down to a 2. But then, if I cube it, I can build it back up into an 8. The 1/2 power shrinks it to a 2, and then I can cube it back up to an 8. Okay, now this looks a little bit silly here. So remember, there is something called the power rule, and we're going to be using it a lot in the next part here. The power rule that if you have an exponent to an exponent, you can just multiply them together. So 3 times 1/2 is 3/2. And that's what we're looking for in that last one. It's a tricky one. In example number 2, we're going to be solving for the n variable, which is within these exponents. But what we're going to have to address first is the fact that we have different bases in the problem. So what I want to be able to do is go back to this idea that if you have a common base, then you can actually just set the two exponents equal together. Logically, they would need to be the same thing. So we have a 4 and we have an 8. We're going to address those first. Okay, so I'm going to think about these numbers, and what I want to do is create a base that they both have in common, but then just raise that base to an exponent that creates these numbers. So in this case, that's going to be a 2. And if you had 2 squared, that's going to give you the 4. And then if you have 2 cubed, then you're going to get to the 8. So I'm going to substitute those in for the bases that we see here. So I've got 2 squared raised to the 6n power is going to be equal to 2 cubed raised to the n plus 1 power. Okay, now the bases are still different though, because you get the 2 squared and you have the 2 cubed. I just want them to be the 2's. So if I go back to looking at this, we can use that power rule. I can take that 2 as an exponent. I can take that 2 and multiply it to the 6n, call that 12n. So this will be 2 to the 12n is equal to 2, and then multiply the 3 to the exponent that's out here. That's going to be done with distribution, so you'll get 3n plus 3. And at that point, let me move that 2 a little bit closer. At that point, because you have the common bases, you can just set the exponents equal to each other. So our problem becomes this. You have 12n is equal to 3n plus 3. We'll subtract 3n from both sides, and you get 9n is equal to 3. You then divide by 9, and that's going to give you n equal to 1/3. Example 3, we're going to start by looking at the 1/2 and the 8 and trying to figure out a common base that they both have. Most likely your thoughts are going to head towards the 8, and you should pick up on that 8 is 2 cubed. So if my base for the 8 is going to be a 2, I want to consider how that could work out for the 1/2. And it actually works out great, because 1/2 is just the reciprocal of 2. So if I take 2 and raise it to a -1 power, that's going to cause that flip and give you the 1/2. Okay, so I'll take these and substitute them in. We've got 2 to the -1 raised to 4x plus 1, which is going to be equal to 2 cubed to the 2x plus 1. We then distribute or multiply, however you want to say it in these cases. It is distribution because you have binomials here, but you're going to multiply your exponents together. And at that point, you can also just drop out your common base. So I'm going to go ahead and do it that way in this problem. I'm going to multiply the -1 in. So that'll give me -4x minus 1. And I'll go ahead and just say that that exponent is going to be equal to 6x plus 3, the product that we have here. That way I'm not writing the 2's and then just removing them immediately, because it's all about understanding where we're trying to go in problems. Since I have a -4x, I'm going to add that onto the 6x and get 10x. At the same time, I might as well just subtract the 3 since I'm keeping my x's on the right. I'll subtract the 3, which will give you -4. So that's a couple moves at once. You then divide by the coefficient of x. So you have to divide by the 10, and that means that x is going to be equal to -4/10, which is the same thing as -2/5. So you can get answers that look like this. This is fine. It's an unusual one. But if you take that answer and you plug it in for the x's, right, go back to the very beginning, use 1/2, raise it to 4 times that number plus 1, figure out what it is. It's an unusual looking number. It's not a whole value. But then do the same thing over here, and you'll see that they turn out to be the same answers. Example number 4 is going to be a little bit different for a couple reasons. One of them, the bases that we're going to look at, I think they just appear to be different than the others. In addition to that, you also have an inequality in there. I'll address that in just a moment. All right, let's go ahead and start by looking at the bases. We have a 3, and then we have the 1 over 243. Okay, so 3 is a prime number. There's not really anything you do with it. It's 3 to the first power. The 243, you might not recognize all these numbers, and sometimes you just have to explore. But you know this is going to be based on 3 because of that number, right? Or even if I had like a 9 or a 27, you would know that it has something to do with the 3. So even though you might not recognize some of the other ones, you know where to begin. Okay, so let's say that I took 3 and I multiplied it 3 times, because I know that's 27. We should all know that. Okay, if I go ahead and multiply by 3 again, I get 81. Multiply by 3 one more time, and I get 243. So that means that there's a connection between that number and 3 to the 5th power. Of course, the fact is that it's a reciprocal, so this is actually just 3 to the negative 5 power. Okay, so getting those filled in, for here, I'm actually just going to rewrite. I didn't in the last one, but I think it might be helpful just to see it all written this way. Actually, you don't need parentheses right there, so let's fix that up. That's wrong too. I'll get there. All right, 2x minus 1, and then the other one, oh, there's your inequality. I'll address that in a minute. The 1 over 243 is going to get replaced with a 3 to a negative 5. Okay, so all that kind of looks weird substituting it in. It's a little bit different than the others, mostly because you don't have as many of the same pieces. But look, the 1's going to multiply to all that stuff, and it doesn't do anything. Okay, and then the 3 with your negative 5, the negative 5 doesn't multiply to anything, right? The 1 didn't do anything when it multiplied, and then a negative 5 doesn't multiply to anything, so you're just going to keep it like that. Now, both of these would have bases of 3, and I'm going to drop those out. The inequality is going to stay the same as it was originally. I mean, we've had other problems in the past where when inequalities were involved in there were these cautions. One of the big ones was if you ever multiply or divide by a negative number, then you need to flip the direction of that inequality. But what we're here doing is just making equivalent statements. We're changing what the bases are and adjusting the exponents to fit those bases. That has nothing to do with what's happening in that inequality. So it's going to stay the same. And in fact, it's even going to stay the same when we drop those bases out and we just set the exponents equal. Here's where it can change. It's not going to in this version of the problem, but if at any point from here on you had to multiply or divide by a negative, then that sign's going to flip. Okay, usually when I do the problems, I avoid even setting up those cases so that I've never have to worry about flipping them. Okay, but here, look, you've got the 2x here, you got minus 1. What we're going to do is add 1 over onto that side. So you get 2x is greater than or equal to negative 4. You then divide by 2, and x is going to be greater than or equal to negative 2. And that's just the answer. Okay, so if you do have an inequality, don't worry about that at the beginning. Just keep that inequality as it is when you set up your exponents, and then if it happens to flip by the way that you do the problem from there, so be it. Most of the time what I do is I make sure that when I have choices of the coefficients, I always make them positive. So if I go back up and look here, I didn't subtract the 6x over and create a negative 10 that I'll have to divide by. I chose to move the negative number to the positive side, creating a larger positive, and then that way when I divided by a positive. So if you have that as a set rule, you don't ever end up in the occasion of needing to flip the sign.